I'm very curious about the next talk, which is given by Gianluca Redondi from the Research Institute Fondazione Bruno Kessler in Italy. And he will tell us about the verification of interlocking logics, which I think are used to model railway traffic.
Yes, yes, thanks. Thank you, everybody. So yeah, I will start with an introduction on interlocking logic. And we are in the railway domain, where we have different components, sensor, traffic light switches. They all interact with each other. And an interlocking logic is a system of rules that ensures safe and efficient operation among those components. And for example, the logic should ensure that no conflicting signals are sent, that switches are set in a safe position, and that no two trains are authorized to occupy the same section of a track simultaneously. Now, in my research center, there is a collaboration with the Italian railway network to develop a tool called AIDA for the design of such logics. Basically, the idea is that the railways engineers can write down system specification in this tool in a controlled natural language. They can write down phrases such as, when a train is arriving, activate some switches. And the tool is able to generate from the specification extended finite state machine for each component of the logic, as well as C and Python code. And the state machine will have states and transition, of course, and transition are characterized by guards and effect, and importantly, effects will cause other transition of other components to fire. Then, once a configuration is given in the tool, and by configuration I mean the map of a specific plant, then you can actually get code ready to be executed for that particular station. So the goal of our research project here is to automatically verify the properties of the logic. Because, yeah, given a configuration, given a particular plant of a station, we could use, let's say, standard model checking to check whether some safety property holds in that particular station. So the properties that we want to prove are no conflicting signals are sent, trains are in a correct position, and so on. But these properties should hold independently from the configuration, and we want to prove them at the logic level. And to do that, we want to generate, alongside the C and Python code, also Dafny code from the specifications, and use a parameterized model checker to automatically infer invariants for the system. So parameterized part here is really important because the system at the logic level is not configured. We have an unbounded number of components for each component type. So to give you a picture of the workflow here, we have AIDA, the tool, and the engineers, they write down the specification in the tool. And then the tool is able to generate C, Python code. So the continuous line here is what we have. And the dashed lines here is what we want to add. We want to add the capabilities to generate Dafny code in a way that when the engineers, they inject some properties, there is an interaction with a parameterized model checker that is able to prove that the property holds in the logic at the Dafny level. And this is all at what we call the abstract level, so no configuration is given. Then if you give the map of a particular station, you actually get some executable code. So in the next few slides, I'll show you some examples of what we have in mind to model the logic in Dafny. Basically, each component will be modeled as a class. All these classes extend a trait, CDL. Each CDL will have a set of, CDL is a component of the logic. CDL has a set of connected entities with other objects that can be affected by the transition of the particular object. We have a predicate filet to define the set, and then we will have a method execute that should mirror the transition relation of the particular object. As an example, here let's have a look at the root class. The root will have a variable state with value in a data type with 4 values. The root will use some tracks, so we have a sequences of tracks used by the root. And in the predicate valid, we see that we state that all the tracks used by the root are in the connected entities, and moreover, all the entities connected to the tracks are also connected to the root. So we have this cascade effect in connection in the logic. And the idea is to have for each transition of the root class in the state machine, we have two methods in Dafny, one method for the guard and one method for the effect. The method for the guards returns a Boolean, which is true if and only if the precondition associated to the guard holds. In particular, here we see that one of the preconditions is universally quantified, so this is mirrored in the Dafny code by a while loop. And we need additional invariants in the while loop, of course, to make Dafny conclude that the body actually meets the specification. But we aim to generate those invariants with the code itself. So via some schemata, we don't need a model checker for this kind of invariants. So this is a method, again, for a guard from a transition that goes from a request state to a lock state. And then we have another method for the effect of the same transition. The method modifies the object itself and the tracks used by the object. And again, we have the requirement, which is the guard of the method, and then the ensures, which are the specification of the effect of the transition. Again, we have a while loop with some invariants, and notably here in the specification, in the body, we have calls to other transition of other components. And this is basically what happens also in the C and Python code generated by the tool. So at the end, each class will also have the execute method that should wrap up all the transition. Basically, the idea is that the execute method of each class will have a bunch of ensures, one for each transition, but the execute method here can modify all the connected entities, so the specification for the execute method should be more sophisticated because we have to state for each of the elements connected to the object how the state changes. For example, here we have to state all the tracks used by the root, they will change the state. All the tracks not used by the root do not change state, and all the other connected entities, they do not change the state when a transition of the root is executed. And the body of the execute method is just a match statement. We have a bunch of cases, one for each value of the state variable. And basically, we fire a transition as soon as it is possible, and we also have some axioms on this state machine that the transition relation is total and fully deterministic. So we know that on each state, there is one and only one transition that can be fired. So to sum up until now what we have seen, we have a design of an interlocking logic in AIDA. We want to generate Dafny code alongside C and Python code to represent components of the logic and their transition. And the idea is that the body of the Dafny methods should mirror the generated C and Python code, whereas the pre and post condition of these methods should be a formalization of the specification of the logic given by the engineers in the natural language. And if we do that already, we have a first result because we have a formal proof that the bodies meet the specification. But remember, this was not the main goal here because we wanted to prove the candidate properties of the logic. And to do that, we need an additional ingredient. We basically have to model the scheduler in Dafny as well. So we define a new class with a set of objects, and then we define a candidate property. And the scheduler will be a method that just picks an object and fires a transition. And what we want to prove is that if the property holds on entry, then after one transition, the property is still true. So each transition preserves the invariant, similar to, I guess, the previous talk. But this, of course, would rarely be the case immediately because candidate properties are hardly inductive on their own. So the idea here is to obtain additional invariants automatically by using a parameterized model checker. But we do not want to go directly to the model checker because model checking, especially parameterized model checking, is very expensive. And so we have designed a Cigar loop, so counterexample guided abstraction refinement loop, where Dafny and the model checker interact with each other if the proof for the property fails in Dafny, then we are able to extract some part of the system that we can model in the model checker, and the model checker finds some invariants, then we pass back to Dafny. And at the end, we either find some successful verification, or we can also find some counterexample by the model checker. So at the moment, we have some early results. We have modeled a simplified case study of the logic with 5 components, 29 transition, and 18 variables. And we can prove that this logic does not allow for 2 different routes to occupy the same section of a track simultaneously. And we can do that by providing to Dafny an inductive invariant that we found by using a parameterized model checker on an abstract version of the logic. At the moment, unfortunately, the Dafny code, the input files for the model checker, and the interaction between Dafny and the model checker are all manual. So we still have a lot to do. We want to obtain Dafny code automatically from the specifications. We want to obtain input files for the model checker as well. And we want to make the interaction between Dafny and the model checker automatically, because right now I'm using Dafny on Virtual Studio Code, the model checker on its own, and doing everything by hand. And of course, once we do these steps, we can make experiments with the actual logic designed by the engineers. And yeah, in theory, we know how to do that, but in practice, I think it will be very hard to implement this feature. And that's it. Thanks for the attention, and I'm happy to receive questions.
Can you go up to the microphone?
Sorry. It sounds like from the point of the domain expert writing the natural language specification, you want to generate everything, including the proofs. Is that right?
The proofs. So we generate the proofs that. So we ask for the engineers to provide the property. The property will need additional invariants of the logic. These additional invariants, in order to make, let's say, the property inductive, we want them to extract those from a model checker.
Right, so and you're hoping to do all of that in sort of an automatic way, right? The point of my question is, I'm just asking whether that is the extent of the automation that you want to get to, and also then my comment is that sounds like a really high bar for automation to get those invariants automatically. But if that's the case, then I think your answer is yes.
We want to start with this goal. With the engineers will have a button. They push the button and they get, okay, your property is true, or no, here's a counterexample. I agree that on the actual logic this will not be feasible, and we probably need to ask the engineers to write some invariants on their own. But it is very difficult because they are not trained in formal reasoning, and also they don't see verification as useful, I think, in these early stages of the project. So we want to, right now, give them something completely automatic, yes.
Okay, cool, thanks.
Since in your project the Dafny code is meant to be generated automatically from another form, I was wondering what you think are the advantages of targeting Dafny instead of Boogie, or even producing your own translation to SMT?
So we actually started by translating directly to SMT. This was very hard for many reasons, and having a object-oriented style programming language is very helpful because it's very close to the internal representation that we have in the tool AIDA. So when the specifications are given, those are transformed inside the tool in basically an object-oriented programming language that it's easier to go directly into Dafny. And then we really, with a one-way SMT translation, this was too big for the model checker to reason. So we kind of want Dafny to be as a shield, let's say.
Thanks.
Hi, thank you very much for the great talk. I was wondering, so the natural language statements correspond to some statements of logic, and what kind of logic you're actually using to specify properties? Is it some form of temporal logic, or what are the, like, what is the system you use to specify those properties?
So at the moment, we want to start with invariant properties. So just every reachable state of the system should have this property. More in general, we need to reason about cycles of transition. So we need to introduce a form of temporal reasoning. But
and following up on this, I would be really interested to see the experiments of trying to translate natural language into temporal properties, because there have been quite some interesting papers of people, I think it was a bunch of people from Brown, looking how difficult it is to actually connect LTL formulas to statements in natural language, and we'll be interested to see how the real engineers, actually when you make them write
but we
properties.
still haven't done that.
Okay. Yeah,
okay, so.
but I'm looking forward to it. Thank you.
Yeah, I'm tempted to ask why you want to do natural language. I'm tempted to answer why you want to do natural language. If you're dealing with engineers, shouldn't they be able to cope with some kind of input language with semantics? People have been looking at railway interlocking for, 170 years? And I bet there are notations such as track diagrams and diagrams for signals that actual railway engineers use, and you could take that as input. Google tells me the Belgians actually have a specification for precisely that.
So I guess I'll dodge the question, just saying I'm, as a PhD student, I was in charge of verification of this project.
Excellent. Blame your supervisor. Yeah.
No, but
Just because ChatGPT-3 is cheap doesn't mean it's a good idea.
I wanted to ask you a bit about the need for different model checkers. I'm not clear whether in the current situation you can check everything you want with Dafny, but you are saying that just using Z3 underneath or whatever. And whether you are saying for some properties it can be that a dedicated model checker will be faster, and what I would like to do is tell Dafny which model checker to use for what. I was not clear about that. And you had a diagram of what does Dafny call. Yes, previous one. Yeah.
so basically Dafny cannot infer invariants of the program. It just checks if the property is inductive with respect to transitions. And in order to get additional invariants for this proof to conclude, we want to use a model checker. In particular,
So it's not a model checker to do theorem proving, but it's a model checker in order to find more properties and then feed them into Dafny so that it can use it when it does its own theorem proving.
exactly, yeah.
Thank you.
One more?
So regarding the CGAR loop, so even if you find more invariants, there's sometimes where you might need to assert some kind of trigger in Dafny to get the proof to go through. You might not get an automatic empty proof. Is that something you ideally want to completely automate away, or is there some expectation in your final goal that you might need to tweak the proof to get it to go through or something?
That's a very good question, since first order logic is difficult. I honestly still don't know, because we know that there is some fragment of the logic which is represented by a first order logic which is still decidable thanks to some alternation of quantifiers and stuff like that. But in general, this is not true. So in general, we still don't know, and we could guess the right invariant, but Z3 basically would not be able to discharge that could happen.
It would be really cool if you could like EPRify the.
Yeah.
Okay, nice talk. Let's thank Gianluca one more
Thanks.
time.